without a business case, technology will not be successful. We always start with the business case, and the business case dictates the people, process, technology that is required to make it happen. So business case first, technology second. And then the solution templates that we provide, we have come up with a library of templates that support manufacturers in their digital journey. It's domain knowledge combined with the analytics required to be successful when it comes to industrial transformation. And then I have just some nuggets of advice on what is the best way to tackle winning return on investment with AI. How can you win ROI with AI in 2 simple slides? So let's start with the business case. The field of IoT is nothing new. It has been around for decades. Maybe the naming has been around for 5 years, but whenever you fly a jet engine, it's being monitored for the last 20, 30 years. So using the cloud, using the internet, using the analytics is not a new field. But bringing it into manufacturing and the level of competitiveness that manufacturing is going through today has pushed governments and organizations to initiate their own initiatives to bring IoT, or specifically industrial IoT, to their markets. So Industry 4.0, or the fourth industrial revolution, was actually a German-born initiative by the German government and the Fraunhofer Institute and several prominent organizations in Germany. And it grew to become a European-wide initiative, actually a global initiative. And in North America, the National Association of Manufacturers, NAM, they actually call it Manufacturing 4.0, or Smart Manufacturing. And there's a Manufacturing Leadership Council, MLC, and they hold a Manufacturing Leadership Summit every year, actually, hopefully in person next year. It's probably the #1 go-to resource when it comes to smart manufacturing in the nation. So that's kind of the equivalent here on this Western Hemisphere part of the world. But Industry 4.0 or Manufacturing 4.0 is all about 4 things. And I actually will start from the right and I'm going to go backwards. 4, 3, 2, 1. What's your ROI? What's your business case? Do you want to improve uptime? Do you want to reduce scrap? Do you want to improve spare parts? What is your why? Why are you doing this? And then we go a little bit deeper. So are you connected? Are you collecting real-time data from the factory floor or from the products, the machines that you're producing, right? Connectivity is key. Keeping in mind different types of equipment, different age, different manufacturers, different control types, CNCs, PLCs, sensors on the machines, right? So connectivity and creating a data lake is very important. Data is the prerequisite to any IoT or Manufacturing 4.0 project. And I'm talking real-time data, not pen and paper data. Analytics. Now that I have data, what do I do with it? So we talk about performance analytics, measuring KPIs like overall equipment effectiveness, the mean time to repair, the mean time between failure of your machines, right? OEE, MTTR, MTBF. You may be familiar with some of those KPIs, but those are performance analytics. Those tell you how you are doing today and how you are doing historically. But then my focus today is around predictive analytics, future performance of your machines, the health of your machine, the remaining useful life of when this machine is going to fail before it fails, the diagnostic of the root cause of the failure. So performance analytics giving you historical insights and predictive analytics giving you future insights to your operation. And then technology, architecture, infrastructure needs, scalability, think big, start small with a pilot, and then I have 10 manufacturing plants, or I have 1,000 machines around the world. How can I have a solid technology foundation for scalability and sustainability of my Manufacturing 4.0? And if you guys run factories, or if you work within a factory, there's always these 4 layers. You got your machines, you got your data acquisition, you got your execution, you got your ERP systems, your enterprise resource planning for finance, warehousing, logistics. But unfortunately, those layers of the pyramid are usually disconnected, or some of them may not exist. Some of them may be outdated. You know, there are challenges. So manufacturing 4.0 and this 4-pillar strategy that I'm showing you here is all about connecting the dots. It's all about IT, OT convergence. You have your information technologies like your ERP layers, and they are not connected to the shop floor. That's your OT, your operational technology. So IT, OT convergence and filling those gaps and ensuring that you don't have silos within your operation is what manufacturing 4.0 is all about. So what's the business case? Okay. It depends on your why, depends on your role, depends on your operation. Here, I'm just looking at a smart factory, okay? But in other cases, you might also have smart products, right? So we work in both the smart factory domain and the smart product domain, but some of the applications I'm gonna show today are more focused on smart factory. So the end user is my factory. It's my plant manager, it's my maintenance manager, it's my quality manager, and the vision is a zero downtime, zero defect operation. I want to minimize downtime to the minimum. I want to maximize quality to the maximum, right? So that's the vision. But in order to achieve that, I need to track metrics in real time. I need to collect data in real time. I need to implement the right analytics for my company. So availability, performance, quality are 3 sub-metrics of a KPI, which is called overall equipment effectiveness. So when I survey my clients today, those are the survey results from around 50 to 100 clients. I don't remember the exact number. And the average improvements they've seen in metrics like OEE, uptime, performance, and quality. Not to mention labor productivity. By automating, by collecting data, by digitizing, you have the capability to reduce paper on the factory floor and improve labor productivity in the operation. And if we go a bit deeper into predictive maintenance and the use of AI and advanced analytics to improve uptime, we're looking not just at reducing unplanned downtime issues, but also marrying some of this data to your PM system. We have clients that run SAP PM, IBM Maximo, Infor EAM, whatever you run. But again, those preventive maintenance systems are usually detached from the factory floor. When a machine goes down, a maintenance person goes manually and creates a work order in the PM system. But if you have a predictive solution on the plant floor, you have predictive insights, you have foresight into what's going to happen to this machine in the future. When is it going to fail? How is it going to fail? And this data can actually integrate to your PM system to improve spare parts, to improve scheduling of maintenance and scheduling of the people, the labor, to actually perform maintenance. So you're going to see drastic improvement in the mean time to repair and the mean time between failure of those assets. We have clients we've seen that have reduced spare part inventory significantly because they were able to have this future view of asset performance and actually reduce the number of bearings and pumps in the warehouse because it's an overhead, right? And have just in time or predictive replenishment of their spare parts, okay? So use case, use case, use case. You know, at the end of the day, it's important to understand what is the why for your business and how you can improve your business, your end customers, your internal customers, but also your external customers, and make sure analytics make sense for what you're trying to do. 2 very quick use cases, and then I'll show some example technologies that can support you here. The first one is focusing on predictive maintenance. The second one is focusing on predictive quality. So in one case, uptime is a big issue. In the second case, quality and scrap is a big issue. Uptime and quality, those are probably top 2 use cases for applying analytics in industry today. When it comes to the first case, this machine or this line makes steel wheels, and the cycle time is quite fast. Every 10 to 15 seconds, a new steel wheel is produced. But the line here, which is in Akron, Ohio, is a very old line. I'm talking 1960s, and I'm serious when I say that. It's making wheels, it's making good wheels, but spare parts are very difficult to obtain because it is a legacy line. It's a very old line. So by sensorizing this line with the right type of sensors like vibration and other sensors, because unfortunately we cannot get data directly from the PLC. The line is extremely old, right? Relay logic. We were able, or this client was able to implement a predictive solution that was providing them health and predictions of the key areas of the line and interfacing with their PM system to actually order spare parts with a 2 to 4 week window. And again, spare parts were tough to obtain, so that allowed them enough time to obtain spare parts for this very old asset and actually fixing the asset before the machine actually fails. So there was a complete transformation from a fail and fix mindset to a predict and prevent mode of conducting their maintenance on a day-to-day basis. The second application was scrap oriented. You know, some of you may be familiar with the casting or the molding industry. Scrap rates are high. The industry norm, I don't know if you know this, but I was shocked when I got to know this. The industry standard norm of defects in the high pressure casting industry is somewhere between 9 to 15%. So if I'm making scrap, 10% scrap on my casting machine, which is probably like a $2 million machine, that's actually considered good, relatively, okay? So we call this project the power of 1%. A 1% reduction or a fractional reduction of scrap on a casting machine on a mid-sized plant, which is around 20 casting machines, was about $250,000 in savings per factory per year. Power of 1%. But in order to do that, analytics had to be implemented to correlate the machine data with the quality data. There is maturity required here regarding the connectivity, also regarding the type of AI that's being used. And it's comparing around 40 to 50 casting parameters to the actual quality of the part. And it's making decisions within 6 seconds, which is faster than the cycle time, whether you're going to make a good part or a bad part, green, red. And actually the analytics were commanding the machine, the robot, to pick up the part and automatically put it in a good bin or a reject bin. So this is called prescriptive analytics. If your analytics are making decisions for you without the human actually being involved and sending data back to the machine to auto segregate the part in a good or reject bin. This is probably the highest level of AI maturity you can have out there. So we talk about digital maturity, right? How mature is your operation? But when you start implementing advanced analytics, we also talk about AI maturity. Because initially I might be doing descriptive analysis, you know, just looking at trends. And then I might start to do some predictive maintenance type. I might start to do some predictive quality type. And then I might start to do some prescriptive analytics type. So there is also a maturity curve for the implementation of analytics in your environment, in any environment. And it is a journey. It takes time. It's a phased approach. There is people, process, and technology components that need to be in place to make this happen. So going back to NAM, National Association of Manufacturers, in 2019, they started giving out an AI Leadership Award. This was the first ever category of AI. And Maxi on Wheels was actually the only automotive client to receive the first AI Leadership Award in 2019. Last year, Boca received it, and hopefully this year more will also receive it. But it's kind of a recognition to how can analytics be used in the right way to drive the right business case for the end user. Right? So what's the technology underneath? There's a lot of solutions out there. I'm not here to preach the solution. I'm here to preach the process. It's 3 steps. The first step is the data lake. You need data. You need real-time data. But you also don't need over-engineered solutions. We don't believe in over-engineered solutions. I'm not going to go into a machine and collect 1,000 parameters to find out which ones make sense. I'm going to go in with domain knowledge and collect the right parameters from the machine, from the controller, from add-on sensors if required, from a camera on the machine if there is an automated device on the machine. And this data is crunched with a systematic process. to ingest the data, make sense of the data, and use AI and mathematics, basically statistics, to convert that data, depending on the use case, into predictive metrics. The first one is focusing on maintenance, which is focusing on the machine itself and the components of the machine. And the second one is focusing on quality, again, if required, which focuses on the part that is being produced on the machine, okay? So I'm gonna come back and talk about asset health, remaining useful life prediction with accuracy, of course. When is this machine gonna actually fail? Diagnostics, what's the root cause of the failure? Is it my spindle failing? Is it my robot axis failing? What's the root cause? And then, am I going to produce a bad part? And what's the root cause for that? Is it my temperature or my pressure signals fluctuating that is leading to my part being defective, right? So data lake, AI, use cases. It's a 3-step process to architect such solutions and to implement them, whether it's in a factory or whether it's outside the factory on a Nordson machine that is shipped to a customer. You know, it's the same analytics, actually, same process, but a different end user. Here you're selling to the plant, and here you're selling to the end user that is using the machine. And this is the process, actually. It might look simple, but there is an analytics workflow underneath. And it is different from machine to machine, or different from machine type to machine type. So for a robot, or for a casting machine, or for a stamping machine, this template will have differences. From the data to the signals and pre-processing the signals, to extracting the features, the statistics that are meaningful to look at here, and then training an AI model, which is data-driven. There's a baseline, and then the baseline changes over time. So baseline data has to be collected to train the AI model. Usually 2 to 4 weeks of baseline data is required in some of the cases I'll show you. And then you need to validate and run the model, usually for another 4 weeks, and then start having predictions, right? Initially, the predictions will have lower accuracy, but as the model continues to collect training data, the accuracy will improve. And you could end up with 90 to 95% accuracies in some of the models. And then diagnosis, right? Analyzing what is the reason for the prediction. So this whole process could actually run in about 8 to 12 weeks if you have the right science and the right understanding of the domain knowledge and how to convert that data and apply the right ML techniques from signal to feature to health prediction diagnosis. So over the years, we've conducted a lot of projects, and we've come up with kind of the top solution templates for industry. So as we focus on manufacturing, you know, I'll kind of focus some examples on those areas. But again, this is not holistic. There's more. You're welcome to email me or drop a question in the chat window or at the end, and I can maybe address some of your specific templates. But robotics, CNC machining, welding, molding, casting, and stamping, and the ancillary components that come with them. So I would say this probably covers 80% easily of the most critical assets and also most expensive assets in manufacturing today. So the idea here is, you know, return on capital employed, right? ROCE. Clients have invested in these assets. They want to make sure those assets run with the best level of uptime and the best level of quality. That's what it's all about. So we never see predictive maintenance solutions as actually a factory-wide solution. Usually there are pockets of critical assets where those solutions are implemented. So if you got a plant with 200 CNC machines, do you really need to put predictive analytics on 200 CNC machines? Most probably not. There are approaches to analyze the maintenance data, talking to the experts in the plant, and it's an 80-20 rule. 20% of those assets are probably leading to 80% of the issues. So we have an approach, and I would recommend an approach to look at criticality analysis, right? Where are the critical areas to begin to maximize the business case? And then following that, scalability of those templates can be put in place. So I have just picked 2 or 3 examples that I'll show you today. One is robots, one is CNC machines, and one is casting. Robots and CNC machines is focusing on predictive maintenance. Casting is focusing on predictive quality. And I think it'll give you a good picture and allow us to stop and ask some questions. I'm going to actually skip the slide. It's the implementation approach. Happy to come back and discuss this with you later. And I'm going to go into the industrial robot template. So it's important to understand that predictive analytics is not going to solve everything. This is not a holistic solution solving all problems. There are specific failure modes that predictive maintenance excels at solving, okay? So it's also important to align expectations and be very clear that if I'm looking at a robot, for example, I can catch issues on each axis of the robot. I can catch the motor bearing failures. I can catch a gear backlash. Maybe if there is a lubrication starvation issue. But I cannot catch a dead battery, you know, my cable failing. So you should not stop doing your PM cycles, you know, your preventive maintenance cycles should continue for these types of failure modes. But predictive maintenance will support you improving your PM cycles for these type of failure modes that are shown in red. So advice number 1, you know, what are the critical assets to start doing your work? Advice number 2, what are the critical failure modes that you should focus on, right? So just always align expectations and understand that predictive maintenance is not going to help you solve everything. It is very specific use cases on where it could deliver the best ROI for you. It's also important to note that, you know, these templates or this template approach could apply to any robot manufacturer or of any type of control. It could be a KUKA, could be a Denso, it could be an ABB. It doesn't matter, actually. What matters is the type of data, the data map, we call it, that needs to be extracted from the machine. So in the case of a robotic, quick example, you know, you can look at the torque current of each axis of the robot. That's a key signal. You look at the angular position, the angular velocity, speed of each axis. Sometimes you look at the temperature of the axis. So those are key parameters. And how do we know that? You know, R&D literature is available for the past 20, 30 years. People have researched robots. Implementations were done on many types of robots over the past 20 to 30 years. So this is not new science. It is taking the best of breed science that has been done in the past 2 or 3 decades and actually making it in an industrialized form that allows manufacturers to start using it today, right? Taking it away from an R&D setting into an industrial applied setting is exactly what's happening as we speak. So then how do I actually you know, view these solutions, right? Again, it doesn't matter the solution you have. My message here is it has to be intuitive for the user, okay? Just imagine, who is the end user here? It is a maintenance manager or a maintenance engineer or a process engineer. Do they have a PhD? No. Do they need a PhD to access and use these solutions? No, they shouldn't. Therefore, the solutions need to be implemented and presented in a very intuitive way, okay? Anybody with a, you know, a high school or an associate degree who is a good maintenance person or a bachelor can go in and look at machine health and understand that it's deviating away from its baseline. You know, click a button that says show prediction and see a prediction RUL. This is the remaining useful life with an accuracy. And then be able to diagnose that this robot is going to fail specifically on joint number 5, right? So I don't need to go fix all the 6 joints. I need to focus on a specific area of the machine that's going to fail, which means I can fix the machine faster. I could keep less spare parts on the machine, and I don't need to replace a good part early. So the early replacement of good parts is actually a big cost and a big hidden evil in maintenance today, you know? When I worked at Toyota 15 years ago, we had a very strict PM schedule. Every 3 weeks, we got to go into each robot. We got 500 robots in the factory. and we have to change all 6 bearings, okay? We have to change all 6 bearings. But then we came to find out that when you look at a bearing, it's actually a good bearing, and we cannot reuse it. We have to scrap it, you know, because it came out of the robot. So the idea here is you got to get the right person to fix the right machine at the right time and fix the right area of the machine before the machine fails, right? That's the whole idea. And then it's significant ROI for the business. This was actually the calculation that we did back in the day. The calculation is still correct. It still works. You just need to plug in your own numbers. X number of robots. The cost of 1 minute of downtime in an automotive plant was $10,000. Number might be less in your area, but still, you know, the power of uptime. You're not making cars in this factory, and 1 minute of not making cars is $10,000. Nowadays, it's like 15, 20K actually. Robots don't fail very often, but there's 30 critical robots that fail every year, and 30 minutes of downtime, do the math, it's like 300 grand for a single robot failure. This is also very important, right? Let's be realistic. Predictive analytics is not going to solve everything. 50% of failures are caught, so 15 out of 30. But if you put in your numbers, and we actually have an ROI calculator I can share with you if you're interested, you can actually come up with your own savings figure for your factory by just looking at uptime. I'm not including here spare part improvement, people improvement, scheduling improvement. This is not part of this calculation, but it is simply just power of uptime improvement. How about CNC machines? Any machine tool, actually. It's a complex asset. This is not a robot. This is not 6 joints moving around. This is actually 4 or 5 completely different components, okay? You got a tool in the spindle. You got the spindle itself in the housing. You got a feed axis, which is the ball screw, XYZ moving in the machine. In some cases, you have more ball screws. You got the gib. You even have a coolant system. The coolant system gets contaminated. And then if you contaminate the coolant, you make a bad part. You got a problem there. So it impacts quality. So nowadays, there are ways to get the data from the CNC control. There are vibration sensors that can be used and mounted on the spindle, which will catch the bearing issues. And it will also catch the unbalance and shatter on the actual tool, which will also may also lead to a quality issue. There are chemical sensors that could be put in the coolant tank, the basin, and you can measure chemical characteristics like pH, oxidation, bacterial growth, temperature, and you can actually make very accurate predictions if the coolant is contaminated and when should you switch the coolant before it leads to defects or issues with the machining, right? So the good news here, gentlemen, and sorry, ladies, if any ladies are on the call, is computational speeds have significantly accelerated and have become cheaper. The cost of RAM, the cost of memory, the cost of storage, the cost of cloud has logarithmically reduced, you know, it went down like this, you know. And the pace of technology has exponentially increased, you know. And therefore, doing the cost-benefit calculations for some of these systems have become extremely lucrative, you know, for organizations to implement this faster, quicker, cheaper, and to get very good results with limited internal IT investments and things of that sort. That's really the advantage of getting a vibration sensor for $200, man. You know, $200 a vibration sensor, a triaxial vibration sensor. That used to be 15 years ago. That used to be 1,000. So that's a 5x reduction in sensor costs. Imagine that, right? But at the end of the day, you need to use the data wisely, and you need to deliver value to your organization, and you need to make sure they have intuitive ways to look at the data. You know, what's the health of my machine? When is it going to fail? In the case of a bearing, the failure is non-linear. The bearing doesn't fail linearly like a robot does. So there is a different prediction algorithm that's implemented here. The diagnosis is also different. I'm looking at the harmonics of the bearing. So this bearing is going to fail at 8,000 hertz. So I'm going to have an inner race failure on the bearing. I'm going to have an outer race failure on the bearing. I'm not looking at a robot axis. This is not a component, you know, diagnosis. This is a a bearing diagnostic of the harmonics that are actually going to fail. We have seen clients that actually take this data and they call SKF or Timken and they say, hey guys, you're sending us bearings that are actually failing due to an interrace failure all the freaking time. Please tell me why. Do I need a better bearing? Do I need a different bearing? Can you redesign your bearing? So it is not just internal use of the data, but bringing in your OEMs that make the machine so they can improve future design of the machine, or making the components so they can improve future component design. That's all a byproduct of these analytics, right? Some say there is, I'm trying to remember a nice sentence, you know, for the IoT, there's a nice expression, you know, like you cannot do it alone, right? There's an it right in the middle. So you cannot do IoT alone, you know? There's an O between I and T. It's a nice expression. I'll send it to you guys. I should put it in the presentation actually. But it's all about partnerships, and it's all about working with your internal customers and external suppliers and even machine OEM makers to improve future designs. Last case study, and I'll close. Casting, even more complex. We went from a low, medium, high level of complexity. Robot, CNC, casting. I got 50 machine parameters being collected for every shot, okay? Every shot of aluminum that goes through, or zinc through the casting machine. I'm collecting 50 process parameters, and I need to correlate them within 6 to 10 seconds, every shot, to the quality of the part, okay? So this needs to be architected in a special way. This is a mission critical system because I have to make decisions every 6 to 8 seconds. With predictive maintenance, I don't need to make decisions every 6 to 8 seconds. My machine is not going to fail every 6 to 8 seconds. My machine could fail in the next 12 hours or in the next few days, right? So less mission critical versus predictive quality, where the AI and the decision making has to work at a very accelerated speed and with more accuracy and more precision. So at the end of the day, this is what needs to be done, right? A AI model needs to be trained with different types of good parts and scrap parts. Scrap type A, type B, type C, type D, right? And the training here takes a bit longer because you need signatures from each type of data type, good and bad. So training may be 4 to 8 weeks here, a little bit longer. But once the models are trained, you actually can make probably 95% plus prediction accuracies on part quality. If you're collecting the right data and it's synchronized to the part and you're able to make decisions fairly quickly. And then the analytics are able to offer what's called auto part segregation. Command the machine to make the decision, and you take the human out of the loop, actually. There's no need for the human to be there making decisions. With the age of the new PLCs and all that, these decisions can be automated. So these quality 4.0 solutions are always active, always making decisions, always prescribing, and also learning from new data to support the organizations. This is just a quick example from an auto tier 1 supplier. These are all the process parameters. But if a process parameter is red, it means, you know, a part has been rejected due to this process parameter being out of threshold. But we are not just looking at each process parameter. We're actually doing a multivariate analysis of the 50 parameters and the correlations between the parameters and using them to make decisions on part quality on the machine. So I wouldn't do this everywhere. I would, again, do this on the quality critical assets or processes in my operation. So hopefully this gave you some hints on what is the why business case, maintenance 4.0, predictive maintenance, zero downtime operations, quality 4.0, predictive quality, you know, zero defect operations. Very quickly, we actually have an IoTco Academy, and we have a course that goes for 7 weeks that goes, you know, 7 weeks deeper into the 45 minutes I just did. And we also are creating an industry certification, which is a 3-session course that also will start to be available April, where people can learn these things over 3 sessions. Each session, I think, is 3 hours of content, so 10 hours of content. That should be released in April. And here's my advice. please don't start here. Please don't start thinking about, hey, which algorithm should I use? What type of data do I need? Should I call Amazon and get more cloud space? Please don't start here. Please start here. People and process. Don't start with technology. Please understand your people maturity and your process maturity before even thinking about implementing AI on any factory floor or any machine. I'm going to be very blunt with the team here. I'm very direct. And people, process, technology is your three-legged stool. The weakest link is as far as you're going to get with these projects, whether it's digital transformation or predictive analytics. And the unfortunate fact is there is usually people and process gaps. And those are usually the reasons why some of these initiatives fail, and it is not technology. Okay. So please consider the change management required to make this happen, the multidisciplinary team, the business case that is needed to make sure these products and technology projects are successful. Set up the right team. There's also the idea of a COE, a center of excellence, we call it. This COE is a multidisciplinary team that includes corporate and that includes plant level champions, and they work in a special structured manner to make sure these projects are successful. Process design, the maintenance process, how is it designed and used today? The quality process, how is it designed and used today? Because by implementing predictive maintenance or predictive quality, the output of that is going to feed into that process, and it has to become an integral part of that process. So our advice is usually people process first, technology third. And at IoTco, we have what's called the Digital Transformation Assessment, DTA. And we go in and spend 2 or 3 days at the plant, and we actually analyze the maturity around people, process, technology, and kind of make recommendations. And sometimes our recommendations are, hey, you're ready to start, let's make it happen. But sometimes, we recommend some gaps where the organization needs to take care before thinking about these solutions. And this is how we do the implementations. I won't go through this today, but there's a very systematic approach to do it. Discovery, design, delivery. We do this every day. It's important to do the assessment, as I had mentioned, and start at the right plant with the right team, with the right number of machines, right? You have to start with the right setup. If we do the setup right, you're going to be very successful in the implementation of a pilot and in the scalability of these projects. So I thank you all for your time. I think we have at least 15 minutes for questions. Hopefully this added value to the audience on the call today. We're very passionate about doing this stuff. We think everybody can be successful regardless of your size, but it has to take the right team, the right people, process, technology to make it happen. We have done a lot of projects in Smart Factory. 80% of our business is Smart Factory. But we have a growing, 20% plus of smart connected product applications where a machine OEM, takes our technology and utilizes the analytics and offers value-added business models, new business models to their end customers. The good news is the analytics are actually the same. The approach is the same, but the end user is different. It's just a commercial structure that we would have to work out. But smart connected products is a growing area of demand for some of the OEMs and machine makers, for example, that we do partner with. And I will share with you my info. If you're interested in the presentation, just shoot me an email, abuali@iotco.com, and I'll email you the presentation.